So when using series element matching networks, what we do is we've got some sort of arbitrarily long length of transmission line. This can be any length we want, it doesn't matter. It could be a meter, it could be 1,000 meters, does not matter. What we then did is we cut open the transmission line. We inserted our reactive element. I'm just showing a capacitor, it could be an inductor. We calculate the value of this. We then insert some more transmission line. This transmission line has a fixed length, and then we've got our load. And if we appropriately choose the length of this transmission line, assuming that it's got characteristic impedance that's equal to the characteristic impedance of this transmission line, and we appropriately choose this value of capacitance, we can match the input impedance of this portion of the circuit to the characteristic impedance of this transmission line. We then made the small change that instead of a capacitor in series there, we could put either an open circuit or short circuit length of transmission line. So we can do that. The problem with both these methods is that we have to cut open a T line. We have to insert this transmission line in series here. And so adding series reactively, or adding these series reactive components can just have some practical difficulties. It's much, much simpler to tune circuits, tune the input impedance of a circuit practically using the technique called shunt stubs, in which an element is placed in parallel with the load instead of in series with the load. So in practice, what you'll use for matching networks are these shunt stub matching networks. When we design these shunt elements, we tend to work in terms of admittance, and the reason is it's very easy to add admittances in parallel. Admittance, as you recall, it's the inverse of impedance, and we can calculate an admittance from just 1 over Z. And so on a Smith chart, we would have normalized admittances. So the normalized load admittance, for example, would be whatever the load admittance is divided by the characteristic admittance of the transmission line, and that's just going to be equal to 1 over the normalized load admittances. And you'll recall, just to refresh you, that admittances have two parts. Y is equal to G plus JB. This is conductance and susceptance, right? And so we'll just do a quick refresher on admittances. And so we've got a 50 ohm terminated transmission line, and it's got two parallel load impedances, and we want to determine the total load impedance as seen by the line. So what this is saying is we've just got 50 ohms, and it's terminated in a load that is 50 plus J100, and then in parallel with that is 50 minus J100. And what we want to know is, well, what's that total input impedance of the load there? And so normally how you would calculate that, you would do Z total is equal to Z load 1 times Z load 2 over Z load 1 plus Z load 2. And so that would be equal to 50 plus J100 times 50 minus J100 divided by the sum So there we go, and if you plug that into your calculator, you get that the load impedance is 125 ohms. Equivalent load impedance there is 125 ohms. An alternative way to calculate that is if we said that the total admittance is equal to the admittance of load 1 plus the admittance of load 2. So that's YL1 is equal to 1 over 50 plus J50. No, plus J100. And that is 0.004 minus J 0.008. and YL2 is equal to 1 over 50 minus J 100, and that gives us 0.004 plus J 0.008. So we see in both these cases the sign of the admittance is opposite that of the reactance there, on the susceptance portion of it at least. And so an inductance has negative susceptance, where capacitance has positive susceptance. So the rules are just inverted for inductance and capacitance when we're talking about them being on an admittance or susceptance basis. To find what the total admittance of the circuit, we just have to then add these two numbers, and we see that those again cancel out, and we get 0.008 mhos, which is the unit of admittance, mhos. And if we wanted to calculate ZT, it's just 1 over YT, which is 125 ohms. So we get the same answer. We'll see for practical reasons when doing Smith chart calculations in matching networks, we tend to work on a susceptance basis or admittance basis.